Welcome to Exponential Growth and Decay, Real-Life Applications of Math 3. The formula for exponential growth and decay is y is equal to a, parentheses 1 plus or minus r, close parentheses, to the exponent of x. So a is the starting or initial amount that you have. R is equal to the percent of change, sometimes called the rate. The percent is always changed to a decimal. So if you start out, they tell you in the problem it's 5%, then you must change that to 0.05 for your rate. If the rate is added to the 1, then the equation is an exponential growth curve. Example, if R is 23%, then you're going to add 0.23 to the 1, and it's going to become equal to 1 plus 0.23, which gives you 1.23. If the rate is subtracted from the 1, then the equation is an exponential decay curve. In other words, if R is 36%, then R is 0.36, which will be subtracted from the 1. So you get 1 minus 0.36, which is equal to 0.64. X is equal to the time that the base is raised to. Okay, so when they give you time, that's going to be your exponent. We're going to compare growth to decay. Growth. In our previous example of 23%, notice that 1 plus 0.23, which is equal to 1.23, becomes our base of the exponential function y equals a times 1.23 to the exponent of x. Base that is larger than 1 is a growth curve, just like the parent function to the exponent of x. Decay. In our previous example of 36%, notice that 1 minus 0.36 is equal to 0.64 becomes our base if of the exponential function y equals a times 0.64 to the exponent of x. A base is smaller than 1 but still positive, then a decay curve like the parent function 1/2 to the exponent of x. Let's look at some examples. We're given the equation y equals 750 with 1 plus 0.03 to the exponent of x. What will our initial value be? That's right, it'll be 750. Is this a growth or a decay? Correct, it's greater than 1, so it has to be a growth curve. What is our percent of change? So our percent of change is 3%. Let's look at the next one. We have y equals 24,000, 1 minus 0.08 to the exponent of x. What is our initial value? That's right, it is 24,000. Is this a growth or a decay curve? You are correct, it is a decay curve. What is the percent of change? Percent of change is 8%. Let's look at another example. Y is equal to 900, 1.27 to the exponent of x. What is our initial value? That is right, your initial value is 900. Is this a growth or decay curve? Yes, it is a growth curve. What is our percent of change? Notice that in order to find the percent of change that we have to subtract a 1 from our base, and we'll see that what we have left is 0.27, which is 23%. Let's take a look at our last example. Y is equal to 0.85 to the exponent x. What is our initial value? There's none. There's nothing in front of our base. Is this a growth or decay curve? Yes, it is a decay curve. What is our percent of change? In this case, we have to subtract 1 minus what is our base of 0.85, which gives us 0.15, which is 15%. So the percent of change on your decay curves, you have to take the base, subtract it from 1, and then that is your percent of change. Let's take a look at this word problem. We're going to buy a new car and drive it off the lot, and the price immediately starts to depreciate or decay. The price of the car was bought for $10,000. It will depreciate 10% annually. Find the price of the car 8 years later. So what is the initial value of your car? That's right, it is 10,000. What is the percent of change or your rate? 10%, 0.10. Is this a growth or a decay problem? Yes, it is a decay problem. What is the time the depreciation is over? 8 years. Place all the numbers in the correct places in the equation, and this is what we get. Y is equal to 10,000, 1 minus 0.10 to the 8th power. In other words, 10,000 times the base 0.90 to the 8th power. Then the car is worth how much after 8 years? Go ahead and plug this into your calculator. That's right. It's worth $4,304.67. All right, we're going to look at another word problem. Buying items that may appreciate in time is a popular hobby, whether baseball cards, fandom items, or antiques. A baseball card was bought for $5 and has appreciated 5% yearly. Find the value of the card 25 years later. What was the initial value of the card? That's right, $5. What is the percent of change or the rate? 5%, 0.05. Is this a growth or decay problem? That's right, this is a growth problem. What is the time the appreciation is over? 25 years. Now we're going to place all the numbers in the correct places in the equation. So y is equal to $5, 1 plus the percent of change, 0.05, and we have an exponent of 25. So what is the card worth after 25 years? Go ahead and plug into your calculator. That's right, it's worth $16.93. Some items are better investments than others. So that is all there is for exponential growth and decay problems. Remember, the rate will be added or subtracted from 1 depending on if you're depreciating, decay, or if you're appreciating, growing from the original amount. The original or initial amount is always in front. The exponent represents time, which may be years, minutes, seconds, months, or days. Thank you for participating. The end.